Hi there, what's up? In this lesson, this is the first part of it, we'll learn about deformation in power systems, transmission systems. And it's a important topic because when you design power transmission, shafts and gears, you need to know how much deformation will happen at the end of that transmission system. So you account for that considering the other design requirements. So what do we mean by transformation in power systems? Uh, it's basically calculating the angle of twist at the end of that gear system. But what we'll do is we'll focus only on like two gears that are interacting or interlocking and transmitting power through them. So let's say gear A here is the driving gear, so it has torque TA, and that's the rotation of the gear A going counterclockwise, and that causes rotation of gear B to be clockwise. And the torque A is transmitted through the gear tooth of both gears in the form of TB. In last videos, we discussed the impact of gear ratio and the ratio between the radius values of the two gears and on the impact, and this impact on the transmitted torque, assuming that the power transmitted is the same with no losses. So there are no losses in power transmission here. So let's analyze here 2 points that meet at the interaction point or the interaction tooth here. So point A at gear A and point B at gear B. And with the rotation of gear A, so A will move and become kind of A prime, and this will result, this movement or this rotation can be tracked by phi A. So it's kind of a movement of the gear. It can be movement due to the actual movement of the gear, or in our case here, it's a static system, so we analyze it just before movement. So we're more interested into that rotation as twisting angle, deformation of the shaft connected to this gear. So if this happens at gear A, and point A was meeting with point B at that interface, and A moves that distance, A prime, the movement of B prime should also be equal. So that movement, that interaction between the two gears, it's causing that the distance travel of a point on one gear is equal to the distance travel of the equivalent point of it on the other gear. So these distances are arcs in the bigger circle here of A and also the other circle B. So an arc in a circle is equal to the radius times phi. Phi is in radians. So if I now track B prime with the same distance, it's now a smaller radius, that will give me a larger phi B because the radius of B is less than the radius of A. And if I can put now the distances B prime and A prime as a function of phi and the radiuses, so I'll end up now with, if I know phi A, twisting or the rotation of the gear A, I can calculate phi B without really tracking either movement, but calculating it as phi A times the gear ratio of RA of RB over RB. Remember that we have seen the gear ratio, but it may be in a flipped way when we dealt with the torque. So TB is equal to TA, but now the gear ratio is flipped. It's RB over RA. But the frequency here is following the same gear ratio that's applied when we calculate the angle of twists. So the frequency at B is equal to the frequency of A times RA over RB. So basically, the bigger gear here will have, when it has an angle of rotation or movement, the smaller gear will move at a faster speed. And because it's moving at a faster speed, so the point will incur or will travel longer distance on its perimeter, which translates into bigger phi, or rotation angle or twisting angles. So let's see that now, this deformation in kind of a little bigger system. So if I have here two shafts, shaft AD and shaft to the left and shaft BE to the right, and there are these two shafts are connected through the gears A and B with two different radius values. So RA is equal to double RB. And what I will do now is kind of figure out what's phi E. So if D is fixed and kind of the shaft DA is supporting shaft EB, so D is fixed. I'm interested, if I apply a torque at E, that will cause how much rotation. So this phi E is the value that I'm looking for. Now, if we visualize the rotation, if torque here is moving kind of, if you look from the top, counterclockwise, so the rotation will follow the torque for rotation of the shaft CE and gear B. Sorry, shaft BE, so the gear B here rotates counterclockwise, but shaft A rotates clockwise. Excuse me. So phi E in this case is equal to, when I calculate a twisting angle of a shaft at a point, I have to relate it to a fixed point. So our fixed point here is D. So phi E is equal to phi ED. So now what will happen is we'll trace that phi ED through this transmission system from point E to point D. So kind of I'm connecting between different distances and points along this path, phi ED. Now phi ED is equal to phi EB, so that shaft EB is twisting, is deforming already because there's some internal torque in it. And beside that, point B is not fixed. So this gear B is not fixed. It's actually dependent and supported on gear A. And gear A kind of already rotates because the other parts of this transmission system deforms. So I cannot say phi E is equal to phi EB plus 0. So phi B has a value. It's not a fixation there. Now the question is, what is the value of phi B? So phi B is dependent on phi A by the gear ratio. So I will take out phi B, plug in phi A times the gear ratio of, that's one mistake here, I will fix. So that's phi A. So RA over RB. Now I know that phi A is equal to phi AD. So phi A, the rotation of gear A, is resulting because the deformation of that shaft AD over length A, and there is internal torque inside that part. And we'll see in other videos how to actually relate the different torques now. But for now, we know that this phi A is not fixed, is twisting because of the twisting of the shaft AD. So at the end here, I can say that phi E is equal to phi EB plus phi AD times R, again, this is RA over RB. And if I want to check if my answer is correct, if I look here, I started with saying that phi E is equal to phi ED. So I start, so in the expanded formula here, phi ED, it's broken down to phi EB, so let's start with the E, plus phi AD, so it ends up with D. So phi AD, ED that I started with is kind of, I expanded it with this formula. Considering that gear B is not fixed, it's supported by gear A, and gear A is not fixed, it's kind of deforming based on that length AD. And that will be the formula that I will kind of use to represent that twisting and deformation through that transmission system. So that was a conceptual explanation of how we trace and track twisting angles and transmission systems. In other videos, we'll see 2 more examples of that. So stay tuned, and I'll see you in these videos. Thank you so much.